All right, we're going to start a unit that talks about polynomial functions, and today we're going to focus on the basic polynomial functions and what we call end behavior. So to start off, we're going to define what a polynomial function is. So the basic definition, a polynomial function, we usually denote it, at least your blue book denotes it as capital P of x, is a function in terms of x, which is only a polynomial. So there's no fractions, there's no square root signs. It's a polynomial of an nth degree. So in this class, we're going to look at polynomials that are higher than second degree, which might be new. Some examples of polynomial functions: f of x is equal to x squared. That's one of the most basic polynomial functions, but it can be anything. P of x is equal to negative 5x cubed plus 2x minus 3. That's a polynomial function. In the first case, this has a degree of 2, and in this one, this has a degree of 3 because it's always the highest exponent. It can be any degree. We could have crazy ones like this: g of x is equal to 8x to the 11th plus 2x squared minus 1. That's still a polynomial function. In this case, it would be a degree of 11. Okay, so polynomial functions, all of them have similar characteristics, which is what we're going to talk about next. So we're going to list the typical characteristics of polynomial functions. In the first characteristic is that both ends extend to infinity. They don't terminate. So, and we're going to talk about this later. It's called the end behavior. The ends of the function are either going to go to positive or negative infinity. Something like that. Okay, positive. Here's our symbol for infinity, just so you have it: positive or negative infinity. So the second characteristic is one you've seen before with parabolas, second degree functions. The roots of the polynomial are going to be the x-intercepts. Only what we're going to do now is a third degree. We're going to look at third degree and fourth degree functions, but it's the same concept. Wherever that function crosses the x-axis, we can find those values by finding the factors and breaking up the polynomial into factors and setting each factor equal to 0. Another characteristic is the fact that polynomial functions are continuous functions, meaning that the domain and range are both just the reals, the set of all reals. And we don't have any issues. We don't have anywhere where things are undefined. So it's a smooth curve. There are no holes. There are no asymptotes. They're just smooth curves and continuous functions. And then finally, the higher the degree, the more complicated the graph can be. If you think of your parabola, your basic second degree function, he's pretty simple. He has one turning point, and he either opens up or down. But the third degree function or a fourth degree function will have more turning points possibly. There's actually a fourth degree function that kind of looks like this. So the higher the degree, the more possible turning points you're going to have, and the more complicated, the more roots, and the more complicated the graph might be. All right, so for the rest of this lesson, we're going to focus on what's called end behavior, and we'll start with some notation first. So we're going to have notation that looks like this: x with an arrow to infinity. And what that stands for, it stands for this: as x approaches positive infinity. So that arrow kind of represents approaches. As x approaches positive infinity. We also have this: as x approaches negative infinity. That's how you would say that. And then we'll also use this with y values as well. So here's what end behavior is all about. Let me just sketch a general graph here. If I have a polynomial function and he looks like this, basically what I want to say is I want to know what's happening to that function, what's happening to my y values as x increases. As x approaches positive infinity, In this case, my y value is also approaching positive infinity because he's increasing in the first quadrant, right? So we would write as x approaches infinity, y approaches infinity. And then look at the other side. As x approaches negative infinity, as it keeps moving off to the left, my y value is negative. So as x approaches negative infinity, y approaches negative infinity. This is just one case, but that's how you're going to write it. If I ask for the end behavior, this is what you need to write. And now we need to work on finding the end behavior without a graph. So we're going to look at different cases for determining the end behavior without having to graph. And all this has to do with when you think about my x values approaching positive or negative infinity, we have to think about what happens with large numbers. So let's say my x value is 100,000. Well, think about how much bigger 100,000 to the 5th power would be compared to 100,000 squared. It would be so much larger. So what happens is when you're thinking about end behavior, when you are dealing with values that are approaching infinity, the only term that matters is the highest degree term, because everything else is like pennies to millions of dollars. Even if there were x to the 4th, x to the 5th would be infinitely larger than x to the 4th when you're approaching infinity. So when we are trying to find the end behavior, you have to remember the only relevant term is the highest degree term. Nothing else matters. Whether it's positive or negative, it doesn't matter. The term that has the largest exponent is the only thing we care about. So when I look at this guy, in my example, I have x to the 5th, 2x squared plus 1. X to the 5th is the only guy that matters when you're approaching positive or negative infinity. So once we have that, we're going to look at x to the 5th. And the two things that affect end behavior are the sign of the term, whether it's positive or negative, and whether my exponent is even or odd. And that's it. So, as x approaches positive infinity, if I put any large value in here, a positive number, and I raised it to the 5th power, I'm going to get a positive number back out. So as x approaches positive infinity, that means my y value would also approach positive infinity. Because if you take any number, 10 to the 5th, going to be positive. Any positive number, like 100 to the 5th, going to be positive. That's all you care about. But what about when x approaches negative infinity? That means my values for x are going to be negative. Well, when you raise any negative value to an odd exponent, the answer, the final value, is going to be negative. Negative 1 to the 5th is negative 1. Negative 100 to the 5th power, going to be a big old negative number. Okay, negative whatever 100 to the 5th power is, some crazy big number. So what that means is as x approaches, I'm going to put a negative sign here, as x approaches negative infinity, my y value approaches negative infinity. Think of the cubic function. The standard cubic function looks like that. It's x cubed, so he's up. A polynomial function that would look like that would look like this. That would be as x approaches positive infinity, y is positive. As x goes negative, y is negative. That's the first case. The second case, let's look at when my value is negative in front. So I'm using almost the same polynomial. My first term and the only term that matters, I have a negative 1 as a coefficient. So again, now I have negative x to the 5th. Well, what happens here? As x approaches positive infinity, I'm putting a positive number in here. I'm raising it to the 5th power, so that keeps it positive, but then I'm multiplying by negative 1. So as x approaches positive infinity, my y value is now approaching negative infinity. As x approaches negative infinity, I put a negative value in here and I raise it to the 5th power. Any negative number raised to the 5th power is going to come out negative, and then I multiply it by another negative 1. When I do that, that means y is positive. I keep forgetting my negative sign there. So the appropriate end behavior for this guy, as x approaches positive infinity, y is now approaching negative infinity. As x approaches negative infinity, y is approaching positive infinity. This function is reversed. It's like it's reflected over the x-axis, which is what our negative symbol typically does. Alright, so now we have our third case. This time I have a positive coefficient and my exponent is even. X to the fourth is the only thing that matters because it's the highest exponent. So we're going to look at that. A positive x to the fourth. Well, as x approaches positive infinity, that means I'm putting a positive number in here and I'm raising it to an even exponent. Positive numbers raised to an even exponent, going to come out positive. So y is equal to positive infinity. What happens when I put a negative number in and I raise it to an even exponent? So if this were negative 1 to the fourth power, my entire value is going to come out positive. Any negative value raised to an even exponent is going to be positive in the end. So as x approaches negative infinity, y is again approaching positive infinity. Think of your parabola. They're both ends are pointing up when your a value is positive, right? Opens up like a cup. Finally, this is our fourth case. We have an even exponent and a negative sign in front. So think about what that's going to be. If I'm going to evaluate negative x to the fourth, think about what happens as x approaches positive infinity and when x approaches negative infinity. Basically, based on the last answer, when x to the fourth is positive, I'm only going to get positive values out. So what that means is it doesn't matter what I put in here. X to the fourth is going to be positive, but then I'm always going to multiply by a negative 1, which means as x approaches positive infinity, y is approaching negative infinity. And the same thing when x approaches negative infinity, y is approaching negative infinity. This is like a reflected parabola. Again, reflections outside the function reflect over the x-axis, so now he's opening down instead of up. So that's the basic intro to polynomial functions and end behavior, and then we're going to look more at this in class.